Friday's class?
Make an announcement at the end about Friday's class.
Thank you. Very helpful. We'll get there. We'll get there. It's a nail biter. You guys have to wait for it and just like, oh God. So let's talk about lecture 2.2, stability from the transfer function. So in the last lecture, notice I didn't talk about transfer function, didn't talk about system representation at all. I just talked about general definitions about the free response and the forced response, right? So let's look at stability from the poles of a closed loop transfer function. From our definitions, in terms of the free response, we see that a closed loop LTI system is asymptotically stable if all its poles have negative real parts. That is, they're in the left half plane. So remember, our systems that have all left half plane poles, or roots of our characteristic equation, or eigenvalues, their free response always decays to 0, which meets our definition of asymptotically stable. So we say that those are asymptotically stable. So we can interpret stability from the poles of the system, or the eigenvalues, or the roots of the characteristic equation. All equivalent, remember. That was one of the things we learned in systems. So conversely, a closed loop LTI system is unstable if it has at least one pole with a positive real part. In other words, in the right half plane, and or has poles of multiplicity greater than 1 on the imaginary axis, which is sort of an edge case, but we have to keep that in mind. So remember, if there's any pole that have a positive real part, that's going to contribute to an exponential growth instead of decrease in the free response. So there's that. Finally, a closed loop LTI system is marginally stable if it is not unstable, but has at least one pole with 0 real part on the imaginary axis, and if none of these has multiplicity greater than 1. There's that greater than 1 multiplicity on the imaginary axis, which is like the edge case to keep an eye on, but it is very rare, so it doesn't happen a lot. Usually you have to have a positive real part for a pole to get an unstable system. That's like mostly the situation. All right, so let's look at stability of a closed loop transfer function from its poles. Given the transfer function below, find the unity negative feedback closed loop transfer function. We call unity feedback the type of feedback that we showed in the previous block diagram, where there's no transfer function in the feedback loop. It's just the feedback is just straight to the command. That's what unity feedback is referring to. And negative means that we do the subtraction instead of addition in the summing junction. So it's standard, just the way that we drew our block diagram in the last lecture, or 2 lectures ago, I guess. Let the command R be R and the output be Y. So we want to find out if this is stable or not from the transfer function. So if we've got, this is our plant transfer function. Let's look at the closed loop transfer function, Y over R, which is Gucci over 1 plus Gucci. And that was what we derived last time, right? Now, I don't mention a controller here. So assume that the controller is just 1, and we'll just say C is 1. If I gave a controller, we would put whatever that is in here. So we've just got G over 1 plus G. Now, if you plug in G that's given, it reduces down to 1 over S squared plus 4, which has poles that are easily found by setting the denominator equal to 0. So I'll say P squared. I'll just plug in P for S just to say these are going to be our poles. You could just use S if we wanted. That's fine. Equals 0. So we want to find out where the poles are, which is where the denominator is 0, which is where the transfer function blows up to infinity, right? Those are the poles. And that gives us the solution for our two poles, P1 and 2, being plus or minus J2. Okay, so they're on the imaginary axis. Let's look at them. Let's look at the complex plane. This is the imaginary axis. This is the real axis. So we have a pole here and a pole there, right? So what can we say about the stability of this system? Stable, unstable, marginally stable, can't tell.
I'd say marginal because it doesn't have positive or negative real parts.
Yeah, so it's marginally stable because we have, first of all, it's not unstable, okay? Because it would be unstable if it had any positive real part poles, which doesn't. It would be unstable if it had any multiplicity greater than 1 poles on the imaginary axis, which we don't have any multiplicity greater than 1. There's not like a double pole here on this spot, for instance. So it's not unstable. It's not stable, though, because we have at least one imaginary axis pole, right? So it has to be marginally stable. So marginally stable. Great. So we did this by actually solving for what the poles are and going back to the definition or the stability criteria that are based on where the pole locations are. So that's a good start. But it would be nice if we could actually identify stability without having to compute what the poles are, or at least have an idea of what stability is before we compute what the poles are. So let's do that. So you can represent the denominator of the closed loop transfer function in either this polynomial form that we are used to seeing, which is this descending order of exponent, or you can have this factored out version, which essentially allows you to see that the poles are like A1, A2, etc. So we can say the following about these two representations. If the system is stable, it must have all left half plane poles. So, 1, all of these A's here must have negative real parts, which non-obviously implies that all of the B's must be positive, and additionally, all of the B's must be non-zero. In other words, there are no missing powers of S. But note, this is not, this only goes one way, okay? So if the system is stable, these statements must be true. But if these statements are true, it can still be unstable, okay? So that's the gotcha we got to be careful of. It only goes one way, the logic. So, however, these conditions on B are merely necessary conditions for stability, meaning that they are necessary for stability but not sufficient. Something more is needed to ensure stability. So, if you're curious about this necessary and sufficiency in logic concept, check it out. That footnote is a very wonderful exposition on that concept, I would say. But it's actually a really important idea in logic, which is necessary and sufficient conditions. So if something's a necessary condition, then if it's not the case, then there's no way that the conclusion can be true. But if it's necessary and it is the case, that doesn't necessarily mean that it will be the case, that the condition follows, or that the result follows, but it's just possibly so. So it actually follows our standard usage, something being necessary, something being sufficient, but you have to kind of make sure you're being tight with your logic up here. So let's look at an example of this. So let's comment on the stability of each of these transfer functions without solving for the poles. G1. I mean, the poles are essentially given to us, right? The A's are all negative. -3, -10, -22. All the A's then have negative real parts, and since they're also the poles, we're kind of essentially cheated and solved for the poles. But these A conditions say that if all of these have negative real parts, then, or I shouldn't say equals, G1 is stable. And you can just see what the poles are from the factoring. We know it's stable. Okay. G2, what can we say about stability of G2? So one of the conditions was that if one of these coefficients in the polynomial is negative, then it's got to be unstable. Okay? So that is well, actually the way I said it, we could say not stable. That's probably a little bit, because actually this one is unstable. If it's negative, it's unstable. If it's 0, it can be marginally stable. So I didn't differentiate between those two, but I'll say not stable. So we know it's not stable. We just don't know if it's marginally stable or unstable, but not stable and stable is the most important distinction. G3. So we have a power missing here, an S squared power that's missing. So one of these B coefficients is 0. Therefore, we know it's not stable, right? And finally, G4, not G6. I don't know why that song just came into my head. So G4, we've got all of our powers are there. We don't have any missing ones. We don't have any negative ones. So what can we conclude? It meets all the necessary conditions for B, right? For it to be stable. But is that sufficient to let us conclude that it's stable? It's not sufficient. So we would say it's maybe stable. We would needs further investigation. And so this is just an exercise in recognizing stability and instability just by looking at the transfer function, not even knowing what the poles are. Just saying, oh, that one's unstable, that one's unstable. This one might be stable, it might be unstable, it might be marginally stable. We don't know. It's not clear from just inspection of the transfer function. We would have to actually compute where the poles are. Or we can use the criterion from the next section, which is the Routh-Hurwitz criterion. Okay, so that's all I've got for today, and I know it's time, so I'll let you go.